Hi everybody, welcome back to Multirate Signal Processing. This time more about the polyphase representation. So last time we saw how to obtain the polyphase representation for the filter and downsampling operation of one filter. We now extend this formulation for a bank of n filters. Here we not only have one filter but n filters in our analysis filter bank, and hence can assemble the n filter outputs or n subbands into a vector of n elements, which we can see here. So this is now our vector containing the signals of the outputs of the n subbands. So subband 0, subband 1, up to subband capital N minus 1. So we also now have n filters instead of just one filter. And we assemble the polyphase vectors of our filters into a matrix in which each column corresponds to an analysis filter. So this is what we can see here. Remember, last time one filter impulse response corresponded to a column vector, and now we have n column vectors. And those n column vectors basically result in a square-shaped matrix, which you can see here. Right. So here in the first column, here the first index is the phase index, again time reversed as last time too, and the second index now gives us the subband. So here the second index is the subband number 0. Then in the next column we have subband index 1, subband 1, and in the last column we have subband capital N minus 1. So each column is one of the n filters. And you can again see the definition of the entries. So the first index is our phase index n, and the second index is the subband index k, and here you can see each of those entries is the z-transform of a downsampled impulse response of the kth subband with phase index lowercase n. Right, so just like last time, just now we have this additional index k for the subband. This matrix of polynomials now contains all our n impulse responses of our analysis filter bank, just like in our block transform case, but now with arbitrary long filters. Right, so here you can see indeed we get this square-shaped matrix like in our DCT or DFT case. Just instead of having only numbers, we have polynomials inside this matrix. Right, we now have a matrix of polynomials instead of a matrix of real or complex numbers. That's the difference. And in these polynomials, we can then pack the extended length of our impulse responses. So if we have an impulse response longer than one block, this then results in a polynomial, which we can basically pack then the extended blocks. Yeah, so this matrix of polynomials now contains all our n impulse responses. So unlike our transform case, here we now have z-transforms, polynomials in z, as our matrix entries. This now enables us to write the filtering and downsampling operation of our entire analysis filter bank as a simple multiplication using the above polyphase matrix. This is a very important result. So here we can see it now. So the output of our analysis filter bank, y of z, in the z domain, including downsampling, is now simply the result of the multiplication of the polyphase vector x of z times the polyphase matrix h of z containing all the analysis impulse responses. So mathematically, this looks similar to the block transform case, but now with z-transforms. Observe that this equation now contains all the samples of our input signal and also our subband signals and our impulse responses, because we use the Z-transformed signals. So even though X is a vector of size n, contains n polyphase elements, its polynomials contain all the samples of a signal. And it can be hundreds of thousands of samples long and can take thousands of blocks. It just means we have high order polynomials, but still we have a vector of only n polyphase elements. Yeah, so mathematically quite compact and simple. Yeah, so the Z-transform converts a potentially infinite sequence into just a scalar or an element, its Z-transform, which can be seen as a 1-by-1 matrix. The Z-transform of that sequence is one big polynomial, so maybe we have a polynomial of order of several thousand. All the input samples are in vector x of z. This is important because it allows us to use longer filters than just one block, longer than with the block transforms, because there we apply the same principle of stuffing all the samples into polynomials using the Z-transform. Yeah, so observe, for an implementation, we can write the polyphase matrix as a polynomial of matrices h of m, like we saw last time, right? So here this h of z is a sum over h of m times z to the minus m. So this is a polynomial where you can see h of m as matrices, which are now the coefficients of this polynomial. So where the elements of the nth row and kth column of h of m are defined by this equation. So here you can see, again, k is the subband index, n is the phase index, and then we have the downsampled kth impulse response at phase n. In Python, the exponent m would appear as the third dimension as slices of matrices. So we saw that last time in the Python example. Here this HP, which would be the implementation of the HM. So here we have block index m, and here we have the matrix indices. Here the phase index n, and here the subband index k, and they contain those elements. So this is how you would implement it in Python. You would get basically slices of matrices where each slice corresponds to one of the m's. So in conclusion, we can write the entire analysis filter bank with its n filters and downsamplers by n with a size n by n polyphase matrix h of z, which is multiplied by the polyphase vector of the signal x of z from the left hand side. So similar for the synthesis filter bank, we apply the same principles. So just as for the block transform case, we can also get the corresponding formulation for the synthesis filter bank. For the synthesis filter bank, we can now also write the reconstructed sequence x hat of n in terms of blocks with index m and phases n, and obtain the synthesis, upsampling, and convolution as this formula, which you can also see in equation 8 of lecture 11 last time. So you can see here's the reconstruction, x hat of m n plus n, and here you can see that we have those two sums. Here's the sum going over the subbands, adding up all the subbands after the reconstruction, and here we have the convolution sum going over the filters of each subband. Yeah, and this contains some still to be determined GK. This is the synthesis filters. So now we can use also the vectors for our sequences of blocks to simplify this equation, using a vector for our reconstructed signal and for our kth synthesis filter. And we start again with looking at just one filter. So here is now our reconstructed signal, It has the same definition as for our original audio signal, just taking blocks of our signal, and M is the block index again. And we do it similarly here for the impulse response for the synthesis filters. And observe here the phase is not flipped. Here the index goes up just like for X. Right, and this is again parallel to or similar to the case of block transforms, where we saw that the impulse response is the rows of the matrix not flipped. So now we can rewrite our synthesis equation as the following, with capital L the length of the synthesis filter. So here we have again the sum over the subbands after the synthesis filtering and upsampling. And here we have the convolution. And now instead of having the samples individually, we have those vectors. Right? Here we have gk, so this reproduces n samples. And here we get n samples as the result. Yeah, and the inner sum here is, this inner sum is basically again a convolution, as you can see here. So you can see the sum over m prime. Here this m prime goes down, here this m prime goes up, and that's basically a convolution that you can see here. Right, and you add up those n subbands and you get x hat, the reconstructed signal. So here we now have no longer our phase index n, because we now have output blocks instead of samples. The inner sum is again a convolution which turns into a multiplication using the z-transform. So here this convolution is turned into this multiplication in the z-domain. And what basically we end up is just a sum over those n subbands. So now we can extend this notation to our bank of n synthesis filters using our subband vector y of z and the synthesis polyphase matrix. Since the output is the sum of all subbands, we obtain our polyphase matrix by collecting all our polyphase row vectors of our synthesis filter gk of z into a matrix, such that the outer sum of the above equation turns into a matrix multiplication. So here we have it. Here's the reconstructed signal. Here we have our n subband signals appearing together. And now this is a polyphase matrix, the synthesis polyphase matrix, which contains all the subband filters. So here we have all the synthesis subband filters, as you can see here. So y times g is then the reconstruction, and g has this form. So each row contains a synthesis filter. So you can see here the first index is now the subband index. Here gk, k is the subband index, and the second index here is the phase index. And yeah, similar for the analysis, this is the resulting z-transform for the entries of the polyphase matrix. So again, it's the z-transform of the downsampled impulse responses at phase n. Yeah, so this is now the synthesis polyphase matrix. Observe that for this polyphase matrix, the indices for the subbands k and for the phase n are in reversed order compared to the analysis polyphase matrix. Right, so here the phase is now non-flipped. In conclusion, again we turned the mathematically very complex operation of upsampling and synthesis filtering into a mathematically very simple operation with a multiplication of the subband vector with the polyphase matrix. So here, same shape as for the analysis. We have this vector y of z, this row vector, times this spare-shaped polyphase matrix for the synthesis. and this results in our reconstructed signal x hat. Right, so now we have this very compact mathematical representation, and now it becomes kind of obvious how to obtain perfect reconstruction, which we will see here. So perfect reconstruction is defined as a reconstructed signal which is identical to the original signal except for a delay, right? So here's the definition with some delay ND at the original sampling rate. This delay usually results from our filtering and the downsampling and upsampling operations. To obtain perfect reconstruction, we can simply take a look at the output of our synthesis filter bank. Right, so here we have the output of the synthesis filter bank, x hat, which results from multiplying y, the subband signals, with a polyphase matrix for the synthesis G of Z. And y again is the result from the analysis filter bank, which is x, the audio signal, times the polyphase matrix for the analysis filter bank. Right, so I just plugged it in here for the y and we get this equation, and you can see we get x hat equals x times h times g. So that means we get perfect reconstruction if h times g is simply a delay in the z-domain representation. So the structure of the polyphase analysis and synthesis filter bank can also be seen in this following structure. So here is a signal flow diagram of the analysis and synthesis filter bank. So from the left hand side you can see my audio signal x of n, here written as in the time domain, although the rest is written here in the z domain, so maybe more appropriately this should have been x of z. But then here we get this blocking. So this is basically what the X2 polyphase program is doing, which I showed last time. So here it takes n samples. So here basically we have n-1 delay elements. So when n-1 past elements appeared and then the newest one arrives, then we have one complete block of n samples. And then those downsamplers let through this entire block and pass it on to this polyphase matrix for the analysis filter bank. So at this point here, we have this polyphase vector x of z. Right. So here, this is what our program X2 polyphase is doing. Similar after the synthesis produces the reconstructed signal x hat of z, again a sequence of blocks. And then we turn the sequence of blocks into a contiguous sequence of audio samples, like the program Polyphase to X, which I showed last time. So this takes n samples, upsamples then by appending n-1 zeros, feeds them into this delay line, and this delay line then operates at the higher sampling rate and shifts them out at the original sampling rate, and after one block is shifted out, the next block arrives, is upsampled and shifted out. Right, so this is basically concatenating blocks for the output. And then in between those two, we have processing at the lower sampling rate. So after downsampling, we have this reduced sampling rate, but instead of processing samples, we process blocks of X. So up to the upsamplers, we have the part which has the much lower sampling rate, which is also beneficial for an implementation, because all the signal processing is now happening at the lower sampling rate, but with parallel processing using those blocks. And here we can see right after we obtain those blocks X of Z, we multiplied with this polyphase matrix H of Z, and out comes the vector Y of Z. Then with this Y of Z, we can have some processing, like for compression, we do quantization, for instance. And after that, in the decoder, we have the synthesis filter bank G of Z, which is basically, again, this multiplication with a G of Z, and we get the reconstructed blocks x hat of z, which are then turned into consecutive samples. Yeah. So the structure of the delays and downsamplers on the left of the analysis polyphase matrix converts a sequence of samples at the high sampling rate into a sequence of blocks at the low sampling rate, also called blocking, which is what our Python function x2polyphase is doing. Conversely, the structure to the right of the synthesis polyphase matrix converts a sequence of blocks at the low sampling rate into a sequence of samples at the high sampling rate, also called deblocking, like our program Polyphase to X. Here we can see that we obtain perfect reconstruction if we have the synthesis polyphase matrix as the inverse of the analysis polyphase matrix times a delay by d blocks. Right. So here we have a delay by d blocks. In general, we can have a delay by some number of samples. It doesn't need to be blocks, but here it turns out to be convenient to just have integer number of blocks. So because then we can just write it as z to the minus d. So that means g of z is simply the inverse of the analysis polyphase matrix h of z times this vector z to the minus d. Right, so here d is the delay at the downsampled rate, because here we multiply it in the domain where we have the lower sampling rate. This is basically again like in our block transform case. This is now the constraint for obtaining perfect reconstruction. The question is, how do we obtain filters for perfect reconstruction? How do we invert a polyphase matrix containing the polynomials? How do we get good synthesis filters? Right? It's not so obvious. So mathematically we know we just need to invert, but the inversion of a polynomial matrix is not so straightforward. A simple approach is analog to orthogonal block transform matrices, where the inverse is simply the transpose matrix. Then it's easy. There the analysis and synthesis filters are identical except for the time reversal for the analysis filters. Remember, this comes from taking the transpose and then the synthesis filters being the non-reversed analysis, the non-reversed entries on the transform matrix, which means the reversed analysis filters. Yeah. The corresponding property of polyphase matrices is called paraunitary. Right? See also the book by Vaidyanathan, Multirate Systems and Filter Banks. And this is defined as the inverse of this polyphase matrix being identical to the transpose of this matrix and then replacing z by z to the minus 1, doing this substitution. So the transposition is the case for real valued coefficients in the polyphase matrix. Otherwise, we need conjugate transposition for the coefficients. So here, this would turn into conjugate transpose. So this definition is very similar to the definition of orthonormal matrices, except that we have the z to the minus 1 on the right hand side, which corresponds to a time reversal. Remember, when we have a time reversed signal, then its z transform has a substitution of z to the minus 1. So this is what we have here. We substitute z by z to the minus 1, which means underlying in the time domain we have a time reversal. The advantage, or rather one of its advantages, of a polyphase matrix with this property is that we don't need to explicitly compute its inverse. We just need to transpose it and replace all z's by z to the minus 1. So it's easy to do. Observe, if our polynomials in the polyphase matrix only have 0th order, only a constant, no z, only z to the 0 equals 1, right? That's the case of transforms basically. Then the polyphase matrix is identical to a transform matrix, for instance our DCT4. We obtain the simple case if our filters are no longer than n, they fit into one block. So this also shows that the polyphase matrix is simply an extension of the transform matrix, or a generalization of this transform matrix. Yeah, and this leads me to the end of this set of slides. Thank you for your attention and see you next time.